So welcome back everybody. So the next speaker this session is Professor Raju Venugopalan. So, Raju.
Okay. These are my third and fourth lectures after the first two. And so if you recall last time, so I'm going to start off where I left off last time. And so what did I do? I constructed a classical EFT, the framework of light front QCD, to describe the physics of gluon saturation, the radial limit, which is the limit of very small x and high energies. Specifically, in the large A limit of QCD, one obtains nearly 2D EFT, for which we can compute arbitrary correlators of gauge fields in weak coupling, which runs as a function of an emergent scale, which goes as a to the 1/3. So when you go to A very large, you see that the scale becomes very large, and hence, because of asymptotic freedom, the coupling is weak as a function of the scale. Now, what I didn't really talk about was that this construction can be extended to finite nuclei because of a very powerful Wilsonian renormalization group method, which allows one to absorb fields into sources systematically with changing x. And I'll mention a few more words about that. But simply put, the large A classical EFT reproduces itself at each value of x with a saturation scale that now doesn't just go as a to the 1/3, but is enhanced by some power, some exponent of lambda times y, where y is a rapidity, it's just log of x. Okay, so this is a power of x to the lambda, where one can compute lambda from first principles in QCD to arbitrary order in the coupling. Okay? I'm cheating a little here, and if you want to know how exactly I'm cheating, you can talk to me later or ask me a question. But the bottom line is that, so you're souping up the scale, so now if this is becoming large, right, then you don't have to be at very large nuclei. But the beauty of this approach is that the classical EFT reproduces itself with each order. And so here's kind of the picture that I want to just outline briefly, is that what I talked about yesterday was about the separation between sources and fields. And I explicitly constructed, how this classical description in terms of a higher dimensional representation of sources arises in this framework, and the fact that they are coupled to these dynamical fields at small x. And I also mentioned that importantly, these sources are static in the light front. Now what you can do is that, if you had some separation at some initial scale, then the scale that I separated the sources and fields was arbitrary, right? I just said, okay, I'm just going to define something as sources and something as fields at some given x. And however, the physics should not care about, the physics just sees the entire hadron, right? It doesn't care what you call sources and what you call fields inside your hadron. So that is the essence of the RG, which is that when you change the scale, right, from one scale x to another scale x prime, the physics shouldn't care about that. Now within the RG itself, what you're doing effectively is that you're taking, what were part of the fields and absorbing them into a redefinition of what you call sources. Okay, so now, the separation is now moved here, and so these fields that you integrated out become part of the sources. And so that increases the strength of your color sources. And that's why you can extend this to finite nuclei. That's the basic idea. Okay? So earlier you needed a very large nucleus to get a large dimensional representation of sources. Okay? However, when you now go to, when you add quantum fluctuations as you change scale to your definition of sources, that enhances the size of your sources. Okay, and that's what extends the validity of this classical EFT to finite nuclei. Okay, and what you get actually is you get a very powerful set of renormalization group equations, which then describe the evolution of these n-body correlators I mentioned that you could calculate in this classical EFT for very large nuclei. Now you can also understand their evolution with energy, okay? So that gives tremendous predictive power to this theory as you probe the hadron or nucleus at different energy scales. And this goes under the name Jim Wilk, and Edmo, who's sitting in the audience, knows all about it, and we'll talk about this in his lectures in great detail next week. The one thing I do want to mention is that one consequence which is going to be relevant for the next two lectures is this remarkable thing that if you look at the classical field, so I showed you this plot yesterday of when you compute the typical momentum distribution, compute the classical momentum distribution in a large nucleus, you got a distribution of the typical momenta that looks something like this, okay? With a peak being centered around the saturation scale. However, when you now have this RG, as I said, the scale grows with energy, so you're moving further and further outward in this axis, so there should be KT here. So you move further and further outwards in this axis, so the typical momentum, harder and harder, okay? So you're always going to be sensitive at some level to what's happening in the deep confining regime of the theory. So remember, the first lecture I said that is really one of the outstanding questions that you don't understand, you know, what the physics that goes on here. But as you move further and further out, for a large variety of final states, one could argue that in the Ray-J limit, the dynamics of what happens here is less and less important. And so this is the entire conceit of this whole framework, okay? That when you get such large scales, that the previously thought to be completely, you know, untractable soft physics somehow becomes tractable. Okay? And this was a big surprise. And this is not something that people anticipated. And in fact, this is also, at some fundamental level, the basis of what's now developed into what one might call a standard model of heavy-ion collisions. It's not a standard model in the sense of the standard model of physics. It's more a standard model in the sense of the standard model of cosmology, okay, where the claims of proof are somewhat more broad, one could say. And so here's the picture that has developed over the last decade or longer, perhaps 2 decades, is that you have this initial description of the wave functions of the two nuclei as being color glass condensates. Okay, so you can describe the wave functions of these hadrons as color glass condensates, and then you can describe the entire evolution subsequently in a series of stages, okay, which one can really carry all the way from soup to nuts to actually describe the multiparticle production that one has, okay? And we will argue in these next 2 lectures that the space-time evolution can be described from first principles in the Ray-J limit of QCD. But, you know, it's important when you do this to realize what the traditional picture of a heavy-ion collision was. So if you went and talked to people in the 80s and told them that, okay, you were interested in heavy-ion collisions, their response would have been this. They would have said, oh, well, you're just colliding, you know, some unprintable words and some other unprintable words. Okay, yeah. Okay. You mean I won't be here, unfortunately, but the rest of the people can remember this. In fact, I think, well, yeah, but I think there was a particular well-known physicist at CERN who used this. Okay, so there was kind of the sense that you're just colliding, you know, stuff on stuff, and you're seeing things. Why is this interesting at all? Okay, so that was kind of the general prejudice that one had to contend with if one said one was interested in this kind of physics. It may still be true, but okay, at least we think that it's not. Okay, so here's this, you know, and some of you may have seen this, but I really love this image here. I don't know if I can play with this. Yeah, you know, you see this very, very, you know, striking thing, right? So that was the traditional picture of a heavy-ion collision, and this is kind of our modern picture. So it's a little nicer than the other image that I showed you, right? You see this beautiful, beautiful image in this very, very sophisticated ATLAS detector of the many thousands of particles that are created in a heavy ion collision. Now, the reason I show this image is twofold. One is to say that regardless of whether one is creating some state of matter in these collisions, what one observes at the end is a large number of particles. Okay? And that's kind of somehow the level at which one should start from. But before I do that, let me address, what people consider to be the signal event of these collisions is that this idea that what you create in these heavy ion collisions is something akin to the state of matter that existed in the early universe about a microsecond before the Big Bang. And this sort of got a lot of press with statements like the early universe was liquid-like and so on. And so this generated a tremendous amount of interest in heavy ion collisions, which to some extent kind of ran against this kind of prejudice that people had about learning something about heavy ion collisions, that the public was excited about the possibility that you could recreate the conditions of the early universe in the laboratory. So what I want to get to in these two lectures is how such a highly non-equilibrium state of matter, right? You're producing these thousands of particles in this very violent collision. And how can that actually form such a quark-gluon plasma, a possibly thermalized state of matter, okay, from first principles. But before I do that, before I get there, let me just digress a little bit to describe a little more, what was the evidence or what were the ideas that formed this claim in these press releases that one had formed such a state of matter, okay, a quark-gluon plasma. And it's not going to be a comprehensive description of that. I think next week there may be one or two talks that will actually discuss more the phenomenology of that. But to just understand this, we have to first understand a little bit what relativistic hydrodynamics is. Now, there's a beautiful example of relativistic hydrodynamics, which is often called Bjorkian hydrodynamics. So that's hydrodynamics in 1 + 1 dimensions. Okay, so you don't have the two transverse dimensions. You deposit some energy density and you study its evolution in one dimension as a function of proper time. So in that case, then, the equations of hydrodynamics are just encapsulated entirely by the time evolution of the energy density as a function of the enthalpy density, which is the energy density and the pressure, and whatever transport coefficients are here. So this is E plus P minus 4/3 of the kinematic viscosity divided by the proper time. So this has the same dimensions as the energy density of the pressure. And the whole thing is divided by tau, right? For just dimensional reasons, you see that right away. Now, statement of the validity of hydrodynamics at some level as a good paradigm is that, as a useful paradigm, I should say, not as a valid paradigm, as a useful paradigm, is that this viscous term is much smaller than the ideal term. Okay, so if the viscous terms are smaller, then hydrodynamics is a good description of this matter. And you can just see from this 1 + 1 dimension example, this term is much smaller than this term. So you take the ratio of the two, right? It's much less than 1. And you see right away that this is much smaller than 1 if eta divided by E plus P, right, which can be written by the first law of thermodynamics as the entropy density times the temperature, right, if this whole thing is very small. Okay. So you see right away that what you get as a condition for hydrodynamics to apply is that eta over S, okay, which is a dimensionless ratio, be much less than small 1. Okay? Because the lifetime tau is roughly, in a heavy ion collision, on the order of the temperature. Okay? So these are roughly the same scale. So what really controls what is big or small in a heavy ion collision is 8 over S. Now, in the early universe, actually, this is quite different. Okay? In the early universe, Quark-Gluon Plasma, 8 over S is actually almost irrelevant. And the reason is the size of the system relative to the temperature is completely different. Okay? It's on the order of 19 orders of magnitude or so. So it's completely irrelevant what 8 over S is in that case. Okay? It's a highly sort of turbulent system that one has in the early universe. But in a heavy ion collision, rather remarkably, 8 over S is what really controls whether hydrodynamics is applicable or not. And that the measure of that is that it should be much less than 1. Now, what is 8 over S? Okay? So it's actually a remarkable quantity to think about it, because if you construct 8 over S in kinetic theory, you find that it's actually the ratio of two fundamental constants. It's the ratio of Planck's constant divided by Boltzmann's constant times the ratio of the relaxation time of a shear that you apply to the system. So suppose you had a system, right? So fluid, and you apply a shear to it, and you see how that shear relaxes in time. It's a ratio of that relaxation time to the intrinsic quantum scale in that fluid, okay, which would be the de Broglie wavelength of that fluid. Okay, so that's a typical scale, also the minimal scale that one could have in the fluid, which is essentially the size of a quasi-particle, right? Quantum mechanical size of a quasi-particle. So 8 over S is actually, from that perspective, deeply interesting. Okay? Because it tells you about fundamental properties of matter expressed in terms of these fundamental constants. So let's look at what 8 over S is in these different fluids. So I have water, I have liquid helium, and then there's two sort of more recently created fluids. One is cold lithium atoms in a trap, and the Quark-Gluon plasma that I just mentioned. Okay? And here's a table actually which articulates their properties very well. So here's again the same four fluids. So these are cold lithium atoms at a scattering length which actually diverges. It's called the unitary limit of the cold lithium gas. And these fluids have different temperatures. So at water is about 370 kelvins. Liquid helium is much colder. It's 2 kelvins. These cold lithium atoms are 10 to the minus 6 kelvins, while the QGP, of course, is on the order of 1 trillion Kelvin, right? Now, the etas are also very different from each other, okay? So the viscosity of water is, in Pascal seconds, is about 3 times 10 to the minus 4. Liquid helium is, much less, as we know. For cold lithium atoms, it's really truly not viscous, right? It's an extremely small eta. But the QGP is extremely viscous, okay? So this is something that people often forget when they say, oh, the Quark-Gluon plasma is not viscous, it's a perfect fluid. You have to be careful what one means, because actually the viscosity is tremendous in the Quark-Gluon plasma. However, the figure of merit for the applicability of hydrodynamics, like I mentioned, is not the viscosity per se. It's the viscosity divided by the entropy density. And that in a Quark-Gluon plasma turns out to be very, very small. Because the entropy density of the Quark-Gluon plasma is huge, as we learned from the talks by Peter Petretsky a few days ago. So it turns out that the coldest matter on Earth that we create in a laboratory, cold lithium atoms at the unitary limit, and the hottest matter flow in an almost similar way. And that's a really remarkable and interesting thing. Okay? Despite the fact that the viscosity of the Quark-Gluon plasma itself, is extremely large. Okay? So it's actually 10,000 times the viscosity of pitch tar. So you have there's this famous experiment in Scotland where they have this, jar where you have pitch tar, and, it's like worse than watching paint dry, right? It takes a long time for a drop to fall. Okay, so the viscosity of the Quark-Gluon plasma is 10,000 times that viscosity. So, as I said, now you should be thinking, right, when I show this, you'd say, what does it mean to have an 8 over S less than 1? Because that would imply that the relaxation time of a shear is less than the intrinsic quantum scale in the fluid. Okay? Now, that's very surprising also from the point of view of thinking about of matter in terms of billiard balls, right? So if you think about the pressure in this room or the entropy density in this room, it's a collection of molecules just scattering, and it's your average velocities that give you the temperature and the thermodynamic properties that you see. And so in that case, then you can really think of, you know, the whatever Debye wavelength of these atoms is much smaller than any relaxation time of any perturbation that you have. Well, in this case, it's the other way around. Okay? But there's nothing that says that kinetic theory has to be valid. That in general. So this is a kinetic picture of what one means. But hydrodynamics, okay, and the properties of matter are much more general than thinking of them purely in terms of kinetic theory. And in fact, there's a really wonderful example, which comes from that of, from holography, in specifically the ADS-CFT conjecture, which, as many of you know, is a duality between strongly coupled n equal to 4 supersymmetric Yang-Mills theory at large 't coupling and large NC, and the duality between that theory in 4 dimensions and classical 10-dimensional gravity in the background of D branes here. Okay, so and so there's a holography whereby you can understand this correspondence as a hologram of this 10-dimensional dynamics here as being equivalent to dynamics that's going on in this boundary here. And what these authors here, well, actually first shown here, was they showed that you can actually derive a value 8 over S in such theories by looking at the classical absorption cross-section of a graviton falling on a black hole. Okay? Actually, in this case, a black brane. And so if you use Kubo's formula for that, if you relate this absorption cross-section to this, it can be shown that this is related to this correlator of the stress energy tensor. And on the right-hand side, this can be related by Kubo's formula to 8 over S. Okay? So if you use this and Bekenstein's formula, which relates the entropy of a black hole to its area, you recover this very beautiful result that 8 over S in units of h bar over the Boltzmann constant, again this fundamental quantity, is 1 over 4 pi. Okay. So this was conjectured then by these authors here to be a universal bound. Okay, and that's now called the KSS bound, and it has had tremendous influence on the development of both ADS-CFT and physics in general, you could say, or mathematical physics. And so what one sees is that, again, in these fluids, you're getting numbers which are comparable to this bound, right? So it's 1 over 4 pi is 0.08, roughly, right? And you're getting something that's a few times this. So what are actually the numbers and how do you get them, right? How do you get 8 over S and how do you conclude this, the statement of this press release that you're forming the most perfect fluid in nature? So if you use 8 over S as a measure of perfect fluidity, which is what this is trying to tell you, is that perfect fluidity is when 8 over S goes to 0, then you can ask yourself, well, how do you see this in experiment? Okay. So, and this is what I'm going to talk about now, is that to imagine this is your heavy-lon collision. So this is an actual event from the star detector at RHIC, where you have produced these thousands of particles. Okay. And so what is seen here is a beam pipe. Okay, so what you're seeing is particles in the azimuthal direction around the beam pipe that are being produced. And now if you decompose the distributions of these particles in terms of the azimuthal angle, right, then you can see that you can actually, so this is what you see, okay? So this is actually an event from the Atlas collaboration at the LHC. So you look at the number of particles as a function of phi, this azimuthal angle. And then what you do is you can say, okay, it looks like a mess let me see if I can learn something by decomposing this into harmonics, okay? So you say d and d phi is some number times 1 plus, just a Fourier decomposition of this. You do this in terms of the cosine. You see that, okay, it doesn't describe the data. Then you try another harmonic. Okay, so you add this V2 here, cosine 2 phi. You see that it kind of gets it much better. In fact, it does a fairly good job of that. But you see there's more wiggles and structures, so you can add V3, and so on. Okay? So in principle, you can decompose this into arbitrary number of harmonics. And of course, how important the harmonics are, how important the size of these are, depend on how well you describe this pattern that you see. So the data can then be decomposed into these harmonics, and the sizes of these harmonics really tell you a lot about the nature of what you're producing, right? That's what's capturing the physics of these particle distributions. And so now, using relativistic hydrodynamics, you can actually compute these harmonic distributions. And so what does a perfect fluid tell you? It tells you that suppose you had some spatial geometry, okay? That was anisotropic in some way, right? It's not a perfect circle here. It's not a perfect sphere. Then if you have some anisotropy, in this case here, then what hydrodynamics tells you is that this anisotropy in coordinate space is very efficiently translated into an anisotropy in momentum space. And the reason is very simple. So imagine that you have an almond, right? And the almond is narrower in one direction than in the other. So if it's narrower, then the pressure gradients in this direction will be much larger than the pressure gradients in that direction. So that will generate an anisotropy in the momentum distribution, right? Because these guys are kicked out much more than these guys going out here. So the momentum of particles coming out this way is much greater than the momentum of particles going on that way. Okay? And so what hydrodynamics tells you is that once you have any kind of spatial deformation, ideal hydrodynamics, then that spatial deformation is very efficiently translated into a momentum space deformation. And the degree to which it does that depends on eta or S. So if you had a very, very viscous object, so think about honey. So suppose you drop a ball into honey, right? What it does is it deforms that fluid, but that deformation lasts for a very long time. Right? It doesn't sort of really bounce back to its original state. So it's while in this case you have some kind of a spatial thing, it just immediately transforms itself into a momentum space deformation. And in fact, you can use this fact, right, to study, the effect of different amounts of viscosity on the harmonics. Okay, so these are hydrodynamic simulations which are viscous divided by ideal as a function of the effect of different amounts of viscosity on the harmonics. So if you have a viscosity, which is this KSS bound, which is 0.08, right, then you see that the effect on these lower harmonics is very little, right, because it's just, it's very efficient. But then you see that the effect changes as you change the harmonic, okay? So it has more effect on the larger harmonics if you take the ratio of 0.08 to ideal, or you take 0.16, it has a much bigger effect. So higher harmonics are extremely sensitive to small changes in eta or S. And likewise, if you had some granular structure inside your fluid, okay, then depending on the size of that granularity, the structure, that also has an effect. So if your granularity is 0.4 divided by 0.2 or 0.8 divided by 0.2, you see that has also a big effect on these higher harmonics. So in principle, you can use a measurement of higher harmonics in this kind of way that I talked about here, right, where you extract this from the data, to really learn about eta or S. Okay? And this is the basis for the statement that you have this perfect fluid. Okay? That you see that, the data, you can extract these Vn coefficients from the data, so that's actual data. And then you see that the Vn coefficients are extremely sensitive in a hydrodynamic picture. So all of this presumes the validity of a hydrodynamic picture. Okay? If you take that assumption for granted, then you find that corresponds to a very small eta or S in that picture, so giving you a self-consistency within that framework. Okay? So the bottom line is that the harmonics of the distribution, right, these Vn harmonics that I mentioned, the azimuthal anisotropies, are extremely sensitive to both the viscosity or entropy. So I was bad, I should have called this the viscosity to entropy ratio, and to the details of the initial state. Okay, what is the granularity of this object? And the smaller the size of the nucleus, the more important these granularity effects become. Okay? The larger the system, these granularity effects become weaker and weaker. So that was my digression about hydrodynamics, right? So I said that what we see from heavy ion collisions, right, is that you seem to be performing a perfect fluid, at least within this hydrodynamic paradigm, which seems to be consistent with the data, and I'll talk about that a little bit more. And so then the question is, how does that happen, right? I mean, you have this collision, and you're forming a perfect fluid. How is it that you actually form this perfect fluid? Okay? What is really causing that? And can one at all understand this from first principles? So I talked in my last lecture about color glass, okay, as an effective theory in the radial limit. And what I'm going to argue is that you can now use this and you can develop a mathematical framework. And the elements of the framework are the same as what Zoran introduced in his talk, but they will, I got your attention. They're the same as what he mentioned in his talk, but you'll see them kind of in a slightly different way presented here. Okay? And so that can be used to understand the initial non-equilibrium dynamics of this matter. And rather than calling it non-equilibrium dynamics, I'm going to call it a glasma. It's something between a glass and a plasma. And so the question is, what are the properties of this glasma matter? And does this glasma actually then become the perfect fluid? Can we prove this from first principles, right? In some way, with some quotation marks around the word proof. So how does this happen, right? So Zoran in his talk, yeah, sure. Okay. So, well, it's just a fun name. I mean, in the sense that it's like, for example, why do you call something Quark-Gluon Plasma, right? It captures some of the essence of the matter that one has, and plasma is just some interpolation between the properties of the matter and the wave functions, right, and the properties of the final state. But in between, you have some non-equilibrium state of matter, right? And so, okay, you want to call it something. I call it the glasma.
No, but when we say Quark-Gluon plasma, so it captures the properties of plasma, right? That's why you call it a plasma. So,
well, it's at some level. I mean, it's a unique kind of state of matter, right?
Okay, I thought that since you were naming it as glass, so it has something to do with some properties of glass, and
it does. So the properties of what you see here depend very much on the properties of this color glass.
Okay.
And so, but it also has features which are those similar to that of the plasma, as you will see.
Okay.
But just think of it as a name I coined, okay, or someone coined. But the point is that I can keep calling it non-equilibrium, blah blah blah. But this object has its own interesting, non-trivial properties, right? So what do you call it then? Okay, it's not something that is exactly like a plasma. It has some qualitative differences to that of a plasma, and it's definitely not that of a coherent wave function and that's being produced. Okay, so there's a form of matter that's being produced. It's definitely matter that's being produced. It has its own unique properties. Okay. And that matter, because it doesn't have an immediate analog to something else that exists somewhere else, I call it a glasma. Okay? Now, if you find that there's some other state of matter somewhere else which has the same properties, then you can call that a glasma too. So anyway, so this is, so let me just say I would call it a glasma. So Zoran actually talked about cosmology And there's actually a non-trivial connection that was really captured beautifully in this nice plot by Tetsuo Hatsuda, where, if you think about the universe, the evolution of the universe, and so it's some closed system that evolves, it goes through some inflationary phase, which is very rapid, the decay of some scalar field, and eventually the scalar field somehow thermalizes. And so it goes through some hot era, so about at 10 to the, at about 10 to the minus 38 seconds or so, and then sort of eventually, about 300,000 years after the Big Bang, you had the decoupling of light and radiation, which led to this, light and matter, where you saw, this microwave background radiation. And what was, of course, the big deal then was that you saw anisotropies in the microwave background radiation, right? It was not symmetrical. And by looking at those anisotropies, you could actually learn about what happened earlier in the universe. So that was kind of really a profound discovery and led to, one Nobel Prize, right? 1990 something, for the discovery, well, actually 2 Nobel Prizes, one for the original discovery of the cosmic microwave background radiation, and another one for the discovery of the anisotropies in the microwave background radiation, and possibly more in future. And what that told you is that you could kind of look back further into the early universe, which you thought was completely inaccessible. Okay? So you could learn by looking at the anisotropies something about the quantum fluctuations in the very early universe that seeded these anisotropies that we're able to see today now. And so there's something analogous here, is that you have this initial coherent state, which then forms this plasma, this non-equilibrium matter that I mentioned, and eventually it becomes a thermalized system, just like in the hot era here. And then the question is, can you look at these anisotropies in this matter that's produced and look backwards in time to understand what the structure of this matter is? And in fact, the analogy gets more concrete than that, is that in the Big Bang, you describe this as a classical field with a very large occupation number, which goes as 1 over the coupling squared, 1 over g squared. In the Little Bang is you have a plasma, which also has a very high occupancy, which is of order 1 over g squared. Now, in the Big Bang, the way the system thermalizes is that you have the explosive amplification of small momentum fluctuations. And so these are quantum fluctuations, which actually are fluctuations around this inflaton. And then there's a parametric resonance between these fluctuations and the classical fields, something called preheating, which eventually may lead to thermalization. And this is not completely understood yet. In the plasma, as I'm going to tell you, there's also a similar kind of explosive amplification of fluctuations, and these are called Weibull instabilities. Again, an analogy to electromagnetic plasmas. Okay? So there's something that happens in the plasma which is similar to electromagnetic plasmas. And then there's a further analogy. It is that we believe, like I said, that it's the interaction between these fluctuations in the classical field which actually de-pairs the system and then eventually leads the system to thermalize via scattering. And likewise, there's something analogous that goes on here. Okay. Now, there are other common features, actually, that in the Big Bang, the early universe is littered with things like topological defects, and turbulence actually is thought to really play an important role in this thermalization of the early universe. And likewise, there are similar things going on in the plasma, which we don't completely understand, and that's really a current topic of study, and I will talk about both of these things in my talk. Okay, so I'll talk about turbulence, and I'll talk about topological objects that you produce in the plasma. And these are both possibly very interesting and important things, and one may perhaps even learn about them in experiment. So, how do you form a plasma from first principles? So, if you have Professor Ravindran here, you will want a certain kind of level of proof of how this occurs, right? So he's going to ask the question, okay, I have these things. Okay, let me think about this as a scattering problem. These two guys collide, and what do, right? So I have these sources here, right, and I have the fields, and then these fields interact, right? The sources are moving close to the speed of light, right? They're valence quarks. So they kind of possibly go through each other. But then they have all these fields, and then I can have all these possible Feynman diagrams, and I can loops and so on. Okay, it's this tremendous mess. How do I compute this thing, right? So this is what Professor Ravindran would rightly be thinking about. Okay? How do you actually even start to think about this problem? Okay, and how do you form this stuff? Okay? So again, here's the space-time picture. Is, like I said, remember I had this color glass as being static sources on the light cone, right, and dynamical fields, right, which are small x modes. So what happens in a collision is that the soft guys, the fields, they kind of get stopped, basically, while the really hard guys, they go through, okay? And what that means is that the really hard, the baryon number in the fluid kind of flows along the light cone, okay? So that goes out to the fragmentation region, okay? So in fact, if you look at the ratio of antibaryons to baryons in the central region of the heavy ion collision at the LHC, it's close to 1, okay? So like in the early universe, it's very close to 1. While most of the baryon number is at the edges. So this picture is well reproduced at very high energies in heavy ion collisions. Okay? So all this baryon matter, all the valence degrees of freedom go here. So all the dynamics that happens in terms of what we think of as thermalized quark-gluon plasma is the dynamics primarily of soft glue that occurs at very central rapidities. So rapidity is a variable which goes from plus infinity along this light cone and to minus infinity along the light cone. Okay? So think about rapidity as an angle along the light cone that goes from plus infinity to minus infinity. Right? So I'm trying to characterize this wedge in some degrees of freedom. So I can do it in transfer space, right, expert, and then I can do it in terms of rapidity, and also I can do it in terms of proper time. So this is proper time. So in this kind of framework, those are the right variables to characterize the coordinate system, which captures the essence of its physics. Okay? So when we talk about a quark-gluon plasma, we think about things happening around rapidity of 0, okay? Because all the baryon number is at either plus infinity or minus infinity, all the soft gluons stopping and producing matter is at close to 0 rapidity. So then, mathematically, the problem in quantum field theory is, how do you compute particle production in the presence of strong time-dependent sources? And the time-dependent is absolutely crucial. So in the color glass picture, what is absolutely important was that these color sources were static in time. Time just drops out of the problem. Okay? When I say time, I mean light cone time, in X plus. That completely drops our problem. And that actually explains why the object remains a coherent state. Right? Because when I have the separation of sources and fields, it would seem miraculous that actually it doesn't decay in time. Okay? So this fact that the sources are static is crucial for the description of this object before the collision as being a coherent state. Likewise, though, after the collision, what happens? So I have one source from here, sources from here and sources of here, they collide. Okay? In the collision, they color rotate at the very least. They emit radiation. That makes them time dependent. Okay? These sources become time dependent. So the mathematical problem in quantum field theory is how do you compute? Okay? In the presence of actual physical time dependent sources. And actually, if you go and open your standard quantum field theory textbook, you'll find it buried in some, in Itzhak and Zuber, there's a beautiful discussion in one chapter, and likewise in Weinberg's book somewhere, I think Pest and Schroeder somewhere too, but you have to go very far in those books to actually find some kind of a discussion. And so, it turns out that the usual formulation when we think about perturbation theory in QCD is not the proper one to think about these problems. Okay? So in that sense, it's a truly profound and interesting mathematical problem in its own right. Okay? Because the physics in this problem is never perturbative. Okay? It's always non-perturbative. So when you think about this kind of physics, just don't use the word perturbative, which I also sometimes fall into doing. It's really whether the coupling in the problem is strong or it's weak. Okay? And that's what actually is a relevant measure to describing what's going on in this dynamics. Okay? So in strong coupling, for example, in QCD, we don't know how to compute at all, right? Because we don't know, there's no small parameter in which you can expand things in. And QCD is such a non-perturbative, nonlinear theory that if you don't have a small parameter, then only the lattice can help you. The lattice is useless for real-time problems, at least so far. Okay. So, but ADS-CFT is possibly helpful because ADS-CFT, the great virtue of ADS-CFT is that it provides a real-time description, okay, of correlation functions in strong coupling that you could compute. And that's what people got excited about ADS-CFT. You could compute eta or S, which is a transport coefficient, a real-time quantity in ADS-CFT. But it's a wrong theory. Okay? It gives you some nice things, but it also gives you a lot of crazy things. And you have to kind of decide what is nice and what's crazy. Okay? And you know, it's still very interesting, and you'll hear lectures next week, I believe, from Johanna Edmenger, and possibly from Michał Heller and Giuseppe Policastro. Now, I'm going to focus on weak coupling here, and the calculations that I'm talking about are very similar in spirit to those of pair production in strong electromagnetic fields, right? So if you open Itzhak and Zubair, the place where you actually just see a kind of nice discussion of this problem is in the discussion of pair production in strong fields, the Schwinger mechanism. Now in QED, alpha is tiny, okay? But to describe pair production, you need very strong fields. So spontaneous pair production, it only happens in very strong fields. And so it's again an example of the fact that using perturbation theory is irrelevant, okay? The coupling is very weak, but you cannot describe pair production in strong fields using that. And it's also similar to the description of Hawking radiation in the vicinity of the black hole, where the gravitational fields are very strong. There's another example, actually, that the people in the gravity world do, which is when you think about the collisions of black holes, for example, when gravity is strong, the techniques that they use turn out to be very similar to the ones that I'm going to articulate here. Okay? So the mathematical techniques are very similar. So again, so there are two clean theoretical limits. Okay, one I said is holographic thermalization in this large Toth coupling limit. And the other, and this is a surprise, yeah.
So in ADS-CFT, the space-time in which the field theory is living is an input to the gravitational equations. So that's the boundary metric of the 5-dimensional gravity problem. So we are not talking of thermodynamics in curved space-time in ADS-CFT also.
Right, but my question to you in turn is, how do you otherwise then describe the thermodynamics of a black hole?
Oh, that is very well-defined subject. But that's a separate question altogether, right? That's maybe I shouldn't take your time.
Okay, good. Okay. So anyway, so what I'm going to be talking about is highly occupied QC. Remember, I said in the class you have high occupancies at weak coupling, and mathematically that corresponds to taking the limit of g squared going to 0, the coupling going to 0. However, g squared times the occupancy is of order 1. So you're looking at very strong fields, even though the coupling is very large. Sorry, the coupling is very small. So this is really, now you usually think this is a strange limit, right? This is very strange, but most of physics is actually in this limit. When you think about cold atomic gases, the coupling is very weak, okay? Except when you go to near the unitarity bound, the unitary limit of the theory. But it's mostly weak. But it's really the occupancy of atoms is very high. Okay, and that's what really describes the physics there. So our focus is going to be non-equilibrium, strongly correlated gluodynamics of weak coupling, and see how far we get. So, okay, so again, the question still remains, okay, how do you compute? Okay? So now suppose I'm producing, say, 1,000 particles, okay? And so mathematically, you would write down a Feynman diagram where you would produce 1,000 particles, okay? And then I would have to cut all possible connected vacuum graphs to get this P sub n, okay? I would actually have to cut n of them, okay, to compute P sub n. And remember, now I'm trying to work in this framework where I have strong time-dependent sources which have large occupancies. So now the complication in this problem is because when you think about a usual amplitude that you compute, okay, some in-out state in the theory, okay, because a vacuum is simple, this is just a pure phase. So when you take the modulus squared, this vacuum-to-vacuum graph, in-out graph, is just unity, so you kind of ignore it when you compute anything in the theory. It's just some normalization factor, which in this case is just 1. However, in general, of course, right, this in-out state can be written as the exponential of all connected vacuum graphs. Okay, so this is a very general mathematical formulation of this in-out state in the theory. And so what I mean by the sum over all connected state is, suppose, let me take the example, which I'm going to work with for a little bit, of a phi cube theory. Okay, it's a simple theory, so for my purposes it's useful now. So I can just write this as a sum of all possible such graphs, right, all connected graphs, which end at these sources here. Okay, so this is all uncut graphs that I can write in the theory. Now, in general, there's something called Katkowski's rules, okay? And I have to admit, okay, that I never understood Katkowski's rules fundamentally until I started thinking about the problems in strong fields. And I thought I was alone in this, but then if you go and read, say, Schwinger's book on source theory, actually, this is actually how he formulates the problem in the first place. But whenever I read textbooks on Katkowski's rules, I always had a hard time really understanding what is it exactly that they meant. And the way to think about it is the following. So imagine you have some Feynman diagram, okay, that you're computing of this. So where you're looking at a vacuum-to-vacuum graph. So I'm looking at this vacuum-to-vacuum graph, right, which has some arbitrary number of vertices and sources, okay, and which are at different, so they are sort of all connected like this. So at different points, okay. And so what you do is that for each such graph, okay, you introduce an opposite set of graphs where you switch all the signs of the sources and the couplings, okay, from plus to minus. So if you have coupling G, you introduce minus G. And so you get a completely corresponding set of diagrams with opposite signs of the vertices and sources. And actually, you can formulate this problem analogous to the way Zoran mentioned in his talk. Although when Schwinger was thinking about the problem, he came to the Schwinger contour, but actually formulating it in this language, and then realizing that it had this equivalent formulation in this sense. And so in some sense, when you're computing some kind of amplitude, right? So you have something time ordered, and then you have something anti-time ordered. Okay? And as Feynman showed us, that you can think of something anti-time ordered as being a particle with the opposite charge moving. So instead of an electron moving forward in time, you had a positron, say, moving forward in time. So generically, you can sort of do this. Okay? And so then there's something called the largest time equation, which tells you that if you take the combinatorics of all vacuum-to-vacuum graphs, okay, and you go through all the 2 to n permutations. So think of a vacuum-to-vacuum graph of n points. Okay, so n different insertions in this vacuum-to-vacuum graph. And then you look at all possible plus minus. So do plus, 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 or plus minus, plus, 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 or plus minus, minus, plus, 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 all possible 2 to the n permutations. And you add all those possible vacuum graphs, right? That will give you 0. And that's called the largest time equation, okay, somehow in the literature. I think it goes back to Landau. But that's just saying that if you have all pluses and you replace it with all minuses, then because you have minuses, you just cancel the 2. It's just a trivial thing at some level. But this largest time equation also tells you that if you just separate out all the pluses, so you just separate out insertions of operators only on this contour or only on that contour, so just only pluses or only minuses, okay, no mixed ones, right? And you take them to the right-hand side, right? Then I can write that equation now as something of this part, something like this here. And so just pluses and minuses. So if this is now a complex object, right? And this is its complex conjugate, right? then it'll be minus twice the imaginary part, right? So let's say I'm adding all the pluses, minuses, plus minuses, all that, and that's 0, right? I just separate out the plus and the minus on the left-hand side. I take the rest on the right-hand side. Okay? So the pluses and the minuses together have real and imaginary parts, and the sum of the two, even I can do that, right? Gives me minus twice the imaginary part. And on the right-hand side, I have the sum of all possible permutations of plus minuses, except the plus plus, all of them, right? And so then also, it turns out that you can define sort of Green's functions which connect these different points, which are plus plus, minus minus, plus minus, plus minus. And I believe you'll hear more about this from Zoran in a different language as he goes along his lectures. But these are the usual Feynman propagators. Okay? So these are the sort of the advanced, so the time-ordered and anti-time-ordered propagators. Okay, and these are so-called advanced and retarded propagators, and these are also sometimes called cut propagators because they, in this case, the particles are on shell. Okay, so p squared is equal to m squared. So now, okay, so this is Katkowski's rules, right? So whenever you see the word Katkowski's rules, this is what it means. Okay, largest time equation, connected graphs, separate out left and right hand side. So what we mean by an amplitude and a complex conjugate amplitude fundamentally comes from Katkowski's rules. Okay, so if you take any graph, okay, and it has all these pluses and minuses and so on floating around, okay, right, all these insertions are pluses and minuses. If you separate out topologically all the pluses from all the minuses in that graph, okay, maybe a complicated topological separation, that is what you call the amplitude for that graph and the complex conjugate amplitude of the graph. So you can actually define what you mean by amplitude and complex conjugate amplitude by this formalism, not the other way around, okay? Okay, so this formalism defines why you take things in terms of amplitudes and complex conjugate amplitudes. If you formulate the theory, you know, right from the start in terms of connected diagrams, all you start is with this, you will recover that I have to think about amplitudes and complex conjugate amplitudes, okay? And the topology of these is what defines this. And there's a whole branch of mathematics, okay, which is devoted to understanding the topologies of these different surfaces, okay, which is, I actually had a student working on this, and I couldn't understand a word of what he was doing. But anyway, it's a very complex problem in topology, actually. I don't know if you know this book by Hua and someone else where he actually discussed this. So anyway, so here's your so now what do we mean by the imaginary part, right, of this connected graph? That's all these possible cuts, okay? And they come with different combinatorial factors which correspond to all the different ways you can cut this, right? So for example, this guy, okay, so you can cut this in all these different ways, and look, there are interesting topologies where I can cut like this, or like that, or like this, or all that, right? It's just a simple problem in combinatorics, yeah.
Very, very dumb question. What exactly you mean by cut in this context?
Cut means that actually I'm putting the particle on shell. So this is, normally would be kind of a plus minus, you know, it would be a plus minus plus minus.
Okay. So this is where you put the plus minus propagate. Okay, good. Thanks.
So actually, now some of you who are paying attention should look at this and say, you are crazy, okay? Because what is it? I've never seen a diagram like this, okay? Has anyone in their sane mind seen a diagram where this thing just kind of spits out something, okay? It violates energy momentum conservation, you can say. I only thought you could produce things when two things collide and two things go apart, okay? But this is where the time dependence comes in, because the source, okay, is a bath of, you know, energy and momentum, okay? And that is spitting out a particle, okay? So in the net closed system, of course, energy and momentum are conserved, okay? But the fact that you have a time-dependent source in there allows you for it to spontaneously produce particles, okay? If this source was time-independent, I cannot have such a diagram, okay? I would be truly crazy, okay? And this is actually what separates the language of coherent states from that of not coherent states, okay? Because this stuff is stable, okay, as a function of time. So if you now take this imaginary part of the connected graph, all these cuts I can write as some sum of something. Okay, it's called a combinant. And this is the probability of vacuum-to-vacuum graphs, all such graphs with any particular number of cuts, and then you sum over all possible cuts. Okay? So that's the full content of the quantum field theory. Okay? Because I can write the vacuum-to-vacuum object, okay, as the sum of all connected graphs, right? And then I take this imaginary part, and then I can cut it in all possible ways. Okay, and remember, I told you that the in-out amplitude, right, could be written as the sum of all these possible connected graphs. So, one can then, on this basis, derive a beautiful formula, if I may say so. And François Jalis and I thought we were the first to actually derive this, but it turned out that something similar was done in a paper by Julassi and Kaufman. Possibly exists even early in the literature, but in our case, we were dealing explicitly with strong fields, and they weren't doing that. But anyway, so one can derive such a formula entirely in terms of these B's. But remember, B's are the probability for cutting these vacuum-to-vacuum graph a certain number of times. So B sub R is saying you cut such a graph R times. So you have, just do the combinatorics. Okay, it's just a simple problem in combinatorics, and this is what you get. And in fact, there's a language which comes from S-matrix theory of Pomerans and regions that can be entirely mapped into this language, okay? So a cut graph is a region, an uncut graph is a Pomeran, okay? And so the whole combinatorics of Pomerans and regions in region field theory can be reformulated this way. So a few observations. First of all, this object is non-perturbative for any n. So even if n equal to 1, even if I'm producing one particle, it's non-perturbative because I have this factor 1 over g squared sitting there. Okay? So if g is large, right, there's no sort of, g small, there's no simple power counting. And even at tree level, this is not a Poisson distribution. Okay? So it's a very non-trivial distribution that you have. So this is kind of a general thing that one can derive. So now you can say, okay, what is it that you were really talking about, okay, in that previous slide? So what I mean is that if I want to compute a probability, what do I do, right? So I have some vacuum state, okay, and I have some state containing 1,000 particles, okay? That's my final state. And there's a beautiful theorem, which is sort of a basis of almost everything that we do in quantum field theory when you compute anything. That's called the Lehmann-Zimmermann theorem, which relates any such amplitudes to the action of some source on this sum of connected graphs here, which is a function of source. So this is what Zorn called J, right? In our case, this would be J, okay, except rho is actually, in our case, a physical source, okay? In quantum field theory, what you do is you add some term, which is J phi, in your action, right? And then you take derivatives with respect to that and then put it equal to 0. Okay? In this case, you don't. Okay? But in any case, what you can see on the right-hand side is n-particle correlation functions of the fields that are inside this mu here. Okay? So this is how you relate an amplitude to a correlation function, or an n-particle Green's function, is through this LZ formalism. So once you have the amplitude, how do you compute a probability? You take the modulus squared, like, of the left-hand side, and then you integrate over all the phase space of the n particles that you're measuring. And that's this P sub n. So now if you have an n particle phase space, there are n such terms in here. So you take those n and you multiply it by these n guys here, right? And then you can rewrite the probability as some object here, d sub n. So think of this d sub n as a kind of Pac-Man that goes and cuts diagrams. Okay? And so there's a d sub n here acting on your connected the sum of all these vacuum propagators. But then at the end of the day, you have to set the stuff on the upper contour equal to the stuff on the lower contour equal to some j here. And so this d sub j is then this cut graph here, the cut propagator, which can be written in this way here, times some derivatives, right, which put things on shell, acting, and then this functional derivative acting on this object here.
Raju, so what ensures that you did a separation, a dynamical separation between sources and the moving graphs? So are the dynamical fields form a unitary basis? Otherwise, like you're separating the sources out, so everything formed a big Hilbert space, and then you're taking these dynamical fields and constructing this LSZ. And what ensures that it is unitary and one can use this Katkowski's rules? And
So that's actually a very, very non-trivial question. I'm not sure I actually know the answer to that. Okay, because I mean, at this stage in the process, right? So I started out overall with some unitary theory, right? So then what you're saying is that, you know, this thing by itself forms some unitary basis. And I think in the case of QED, it's the fact that, at least in this context, I believe it's the fact that you can actually use the parton model on the light front. Okay? In the parton model on the right front, you have a simple decomposition where both the interacting fields and the non-interacting fields form actually a good basis.
okay. It's like some kind of block diagonal kind of.
Yeah, you can actually block that. So that's a very good question. Okay, let me think some more, and I'll. So anyway, so you have. So suppose you now want to compute something called. So remember, I said the probability to produce even one particle is arbitrarily complicated, and you say, well, this is hopeless, and this is actually why someone would naively think it's hopeless to compute n particles in this case, because you have this huge factor here. But it turns out now that you don't need to compute the probability for objects of interest. Okay? What do I learn from computing the probability to produce 1,000 particles? If I want to understand the properties of the matter, it's not obvious. What I want to study is 1, 2, 3 particle inclusive correlation functions to understand the properties of the matter. And that, what I mean by that is I want to compute the average number of particles that I produce. I want to produce the average number of the product of two particles at two spatial positions, and so on, right? I want to compute n particle correlations, because that's what's going to tell me about the properties of the matter inside. If I just measure the probabilities, it's going to just tell me of the asymptotic states at some level. So I'm not really necessarily learning anything in that process. So what I really want to learn is the average probability, which is n times p sub n, and the sum over all n. It turns out that using this formula that I had here, right, I can rewrite this d as some e to the d acting on this connected product of connected Wilson lines, connected vacuum-to-vacuum graphs and a complex conjugate amplitude. And this is what is then called the Schwinger-Keldysh amplitude. Okay? So this object is what then, in formulations that one has, like path integral formulations, it becomes this Schwinger-Keldysh amplitude. And so you can actually, and the point is that this translates for all n-inclusive distributions. So I don't need to work with connected-to-connected graphs anymore. I can work with the Schwinger-Keldysh connected graphs, defined on the contour. Okay. And so then the average multiplicity from this expression can be written as this cut propagator, which is acting on this product here, where this is now defined as the derivative of the connected vacuum graphs with respect to the sources, right, where now the sources in the upper and lower contours are set to be equal to the same. Okay, so there's gamma plus and gamma minus. And that corresponds to, again, the source emitting one particle on the amplitude and emitting a particle in the complex conjugate amplitude. But then I can also have the case where it actually produces two such particles, which are then cut in this way in plus and minus. And that corresponds to a second derivative of this vacuum-to-vacuum amplitude with respect to the sources. So now, to leading order in this mathematical formalism in strong fields, the inclusive number of particles is just the product of producing, say, one such particle in the amplitude and another such particle in the complex conjugate amplitude. So this is plus being produced in the amplitude, in the amplitude and minus in the complex conjugate amplitude. That's what I define by saying that I have amplitude or complex conjugate amplitude. At the end of the day, I have a plus or a minus being separated from each other. So it's either on the upper contour or on the lower contour. Now, however, all these intermediate steps here can have either plus or minus. So I have to sum between, so if I start from plus, this can go from plus to plus or plus to minus, and then it go from plus to plus or plus to minus, and so on. Okay, so I have to add up all the intermediate pluses and minuses when I do this. And when I do this for each graph, it turns out that computing this average inclusive probability is the same thing as solving the classical equations of motion with retarded boundary conditions. Okay? So this object here is just the product of the classical equations of motion as a function of x times the classical equations of motion in terms of y, right? With this initial with retarded boundary conditions at minus infinity. So this very complicated problem, right, of producing n particles, I transformed it into something, right? Now can compute average inclusive particles and correlations of those. And I retranslated that into a problem of solving classical equations of motion. Okay? So similarly, I can also do this to higher orders, okay? So by the way, this calculation was to lowest order in G, but all orders in G row. I could have arbitrary number of rows that I'm inserting on here. Okay? So when I'm solving this, even for the single inclusive probability, it's an extremely complicated calculation. Okay? If I'm trying to compute all the diagrams, it's very, very complicated. So it's this amazing miracle, in a way, that you can rewrite this as a solution of classical equations of motion. So this very complicated probabilistic calculation simplifies tremendously. However, I can also, in this approach, I can also systematically go to higher orders. I can do an NLO, NNLO, and so on. And so NLO, for example, will be order G to 0, but all orders in G row. And again, I can write down my inclusive average multiplicity as a sum of these kinds of graphs, where I now have two particles being produced and I integrate over one of them. Okay? Or I have this cut here again in between amplitude and complex conjugate amplitude, but I have a loop in one of the guys here. Okay? So this is formally NLO. And I can think of this object as coming from quantum fluctuations in the background field, the product of those, averaged for all sources. Or I can think about this as a product of a classical field here times the one loop correction to the classical field here. And in principle, I can go to N and LO and so on. So I can do this calculation. So just like in usual perturbation theory, where I'm doing things in the vacuum, I can also do this in weak coupling to all orders. Okay? But this is not standard perturbation theory, right? Because I also have this resummation going on at each order, what I'm doing. So one can now say, now suppose I have two nuclei, right? This coming back to this heavy-ion collision. Right? How do I compute, say, some operator, some inclusive operator now? It can be either the average multiplicity, or it can be a two-particle correlation, or a three-particle average, inclusive quantity. So there's a theorem which says that because all that matters, right, is I'm thinking in terms of these classical fields and fluctuations around them now, then to compute this operator, right, the object, again, I can formulate this problem entirely, as I mentioned, in terms of retarded boundary conditions. I don't need to know about the future boundary conditions now. I've reformulated this problem of inclusive average multiplicities in terms of initial conditions that are specified minus infinity, and I evolve forward. So that's the equivalent thing to what Zoran was talking about in his lectures. I don't need to think about, for inclusive quantities, I don't need to think about boundary conditions at plus infinity. The problem can be mathematically reformulated exactly into specifying data on some initial surface at minus infinity. So all I then need are retarded propagators to actually advance into the forward light cone and compute something there. So it turns out that you can actually formulate this object that I'm computing at next to leading order. So at leading order, it's just a product of classical fields, okay, that I compute here for the average multiplicity. The multiplicity at next to leading order can be written in terms of a propagator, which I define on some initial surface here, okay, which is before the collision. So suppose a collision happens here. I'm defining some initial surface before the collision, Okay, and if there's no time evolution of these fields afterwards, okay, that's important. So these are just static fields. Then all that matters is the initial data on this initial surface that I have here to compute something in the forward light cone. And so for that, I need to have the one-point function in this background field. That's this beta here. So that's a one-loop correction to the classical field. Or I need a two-point function in this background field. But this is formulated on this initial surface, right? And this, amazingly, this at next to leading order, the NLO correction to this operator here can be written as the leading order operator here times all this non-trivial one-loop information which is formulated on this initial surface before the collision. Okay? And that's the remarkable thing. I don't need to follow this all the way. Okay? There's a complication. So in other words, and these t's here are just linear operators, right, which are defined as a function of these u's, which are spatial positions of this initial wedge that I have here. So in other words, the initial functional derivatives, right, which are these t's, act on these operators at a later time, okay, and they define then the evolution to that later time. So these are defined on what's called the initial Cauchy surface. Okay. Now you can show, right, that the contributions which cross the two light cones. So imagine that I have a collision of two nuclei, right? You can ask me the question, how come there are no quantum fluctuations which talk to the two nuclei before they collide? Okay. Here I'm formulating everything in terms of retarded boundary conditions. It's just the evolution of the nuclei up to the point they cross, and then they cross, right? But you can ask me, well, in quantum mechanics, I could have a fluctuation which talks to these guys as they're approaching each other. So what do you mean by talking about these two nuclei in the first place, right? And so you can show that these kinds of quantum corrections which talk to the nucleus coming along this wedge or the nucleus coming along the other wedge are actually suppressed. At least to leading logarithmic accuracy, we can prove that. Okay. And then there are contributions in this wedge which are actually power suppressed in this little diamond here. And this derivation of this factorization theorem is very similar in spirit to the factorization theorems that you heard about from Michael Spira in his talk. Okay, so he didn't actually prove them, but he alluded to these factorization theorems. In fact, when I was talking to George Thurman about this stuff, he said they were thinking entirely in this language of classical fields. Okay, when they were deriving these, I mean, that was kind of the intuition that they had. And in terms of, they were thinking in terms of Weizsäcker-Williams fields which were colliding and understanding how the quantum fluctuations between these actually talk to each other. Okay? And it turns out that this is an exactly equivalent formulation, at least to leading log accuracy. And so you can factorize the fluctuations that are going on in here, in this nucleus, right, from the fluctuations that are going on in this nucleus. And it turns out that this NLO operator here in the forward light cone can be written in terms of the Jim-Wolk-Hamiltonian, right, that I was telling you about, which gives you the RG evolution in each nucleus, separately acting on the evolution in this guy, okay, and in this guy separately. Okay? So then I have a factorization theorem which tells you all the quantum fluctuations, right, can be absorbed in the evolution of each of the nuclei before the collision. Okay? That's the mathematical statement. Okay? But that's described by these weight functionals, not PDFs. Okay, so it's a much deeper factorization in the sense that it includes all these higher twist contributions that I was mentioning yesterday in my talk. Okay, so anyway, so what do you find at the end of the day? So I'm sorry I went through some of this mathematical sort of verbiage, but the point is that I want to show you that there is an actual mathematical framework in some limit, okay, that formally tells you that there is a kind of deeper factorization that goes on, okay, than what one usually thinks about in terms of just PDFs, okay? And this factorization is what one would call Jim-Wolk factorization, where if you compute some inclusive, so suppose I want to compute the energy density of the Quark-Gluon plasma, okay? So suppose I'm calculating, you know, what is it that I'm interested in the Quark-Gluon plasma? I'm interested in the energy density. I'm interested in correlators of energy densities. Those are not probabilities. Those are inclusive distributions, right? What is the energy density? It's the energy times P sub n, right? Or P sub E, or Pn of E, if you like, summed over all that, right? So you're not interested in probabilities, you're interested in inclusive quantities. So if I ask the question, what is the energy density of the quark-gluon plasma? The energy density, that's the, this is the stress energy tensor, right? So I can ask a question about any component of the stress energy tensor. That, it turns out, has this kind of factorization, okay? Where I can evolve all the quantum fluctuations in each of the nuclei in terms of these weight functionals. Remember yesterday I showed them to you, they were these Gaussians and rows. But they have this evolution now with Jim Wilk. Similarly for the other nucleus, times the leading order energy density, okay? So I'm including all these, loop corrections which are of leading log accuracy. I'm absorbing them in this, in these weight functionals in one nucleus or the other nucleus for a given source distribution, right? And then I have to average over all possible source distributions of this object. This will also be a function of rho, by the way. So one has mathematically shown to some order that you can actually compute this. Okay? So I'm almost done. Okay? So essentially, Glasma factorization is a product of these universal density matrices W that you can actually, in principle, extract from deep elastic scattering of nuclei, and you could use in computing things in heavy-ion collisions. But these objects are much more complex than the PDFs that you measure. Okay, they contain information. They're really density matrices, or at least components of density matrices, which contain a lot of information. Okay, and this is, if you like, your matrix element that you compute. So, can I have 5 minutes? So. Okay, so this part is going to be less heavy. It's just going to be kind of lighter. So it's kind of the downshift. Okay, so don't worry. So remember, I said that I need to compute this object as a function of rho. I average over the source distributions in rho, then I can compute the energy density. Okay, so this is some Gaussian, say, in rho. This is another Gaussian in rho. I have to solve the classical equations of motion, right, for given rows, and then I average over all rows, and that gives me information that includes a lot of quantum physics as well. Right? Yeah. Okay.
So firstly, you said in the beginning about this Katkowski rules and to compute multi-particle production. So in that case, you are taking the functional differentiation before doing the integration over the sources, is it?
So what I'm assuming is, so usually what you do, that's correct. You functionally differentiate with respect to rho to get a correlation function, right? But then you don't set rho equal to 0, right?
Yeah, with whatever the sources.
Rho is whatever its value is.
And then you integrate over the sources.
Then eventually I integrate over the sources.
Yeah, but then I'm a bit confused because when you talk of this Jim Walk evolution, essentially you are integrating out some faster sources and coming to, like you are changing your XC, the cut of X or something. So how does this commute with, so I'm just a bit confused about the consistencies.
So very good. So it actually also, my answer will address part of what this very nice question that Sayantan asked, which is all of what I showed before, right? In terms of this phi cube theory and all the cut diagrams and so on. That's for one fixed configuration of sources, right? So I'm saying think of the path integral that I wrote down as a path integral for a fixed distribution of sources. Okay? So in that sense, you can understand the quantum field theory of the gauge fields as being completely unitary. In that sense. So it violate your condition. But then, at some point, my problem, right, is then given multiple such sources, right, because in the physical quantity that I'm computing at the end of the day is colorless, right? So each such source has some color charge distribution, if you like, right? But I'm saying for a given color charge distribution, I can couple this to my QCD Lagrangian. That evolution is completely unitary, okay? And then I'm taking different such distributions of sources. But the time scales of those sources is much longer than the time scales that I care about that other stuff. Okay, so it's like the replica argument here, right? In the sense that I have some impurity in the system, and then the dynamics of the spin fields is, and then at the end of the day, I have to integrate over all the possible impurities that I can have in the system.
So essentially what you're saying is that you first integrate over the sources a bit to define a theory at a particular scale. And then you take then of course in a specific source configuration you are having a time-dependent Hamiltonian which is unitary because the time evolution is unitary given in terms of those source fields.
Exactly.
And then in the end you do it. So you have to do it. This has to be done in a specific order.
Exactly. But what I'm saying is that, and that's why I said, so assume that at my leading order, right? So assume I make an arbitrary, in each of the two nuclei, I have an arbitrary X scale, okay? Which corresponds to my scattering. And there I have some sources, right? Some rows, right? And then I have some fields. Okay? Now I have the collision. I do the same thing. I have an LO description, and then I do the NLO description on top of that. Okay? And the whole point of this factorization is to argue that that can be done, okay, in such a way that it can be done already at this level of each given sources, each given of these sources. And then I'm just absorbing. You remember, I'm doing all this absorption in the backward light cone. Okay, I'm doing nothing. I'm saying that the computation of an operator in the forward light cone, right, has nothing to do with what's happening here. It's all happening here. This is an absolutely non-trivial thing. Okay? And we can only prove it to leading logarithmic accuracy. Okay? It may very well break down when you go to higher orders in perturbation theory. Okay? It's something that has to be proven. Okay? It would be an absolutely tour de force if you can prove this actually to higher, either to higher order accuracy in X and also in powers of P+. Okay? This is completely non-trivial that you can actually show that. Okay? But it really relies on the fact that you can formulate all the initial data that you require for computing and operating a forward light cone, okay, on this initial wedge. Now, the start of my next lecture is to tell you that I've been lying to you, okay? But I will start my next lecture by saying I'll be lying to you, okay? Because what I'm saying is not entirely true. And the reason it's not entirely true is that there are two classes of quantum fluctuations. There are classes of quantum fluctuations which are static in time, and these are the small x fluctuations. And for those small x fluctuations, I can do this factorization. But that's what gives me my energy evolution in the first place, right? I mean, because remember in the color glass, all the quantum fluctuations that I have, I didn't actually talk about it, but Edmond will talk about it. Those are static in time, in x plus. Okay, so those quantum fluctuations then can be absorbed, and they give you BFKL, Jimble, PK, whatever you want, right? So that's stuff. But there's another class of fluctuations, and that's the topic of my lecture, okay, next lecture. Okay, and that generates some very interesting stuff. Okay? We can continue this discussion, but let me just very quickly sort of mention some of the consequences. And then, so the point is that my claim, right, and it's a very non-trivial claim, is that you can understand things in such a way that the leading order thing is just computing the solutions of Yang-Mills equations with some sources. By the way, if this were not true, anything that's being done and anything that you hear about all this phenomenology in terms of all this stuff is totally not appropriate. So what you're doing then is the solution of Yang-Mills equations, which correspond to solving here on the left-hand side, d mu f mu nu, in terms of now two light cone sources. Okay, so one is rho going on one light cone in P+, and this other guy is going on the other light cone in P+, and they have some source distribution of color charges at some given scale in X. Okay? So this is some rapidity-independent object because it's just any possible X that you can have. And now these rho correlations are given by this QS scale in each of the nuclei separately. So I have a QS for this nucleus, I have a QS for this nucleus. Okay? And you can actually obtain this from, do phenomenology and obtain QS from saturation model fits to Hera, like I briefly talked about yesterday. Okay? So you can then actually go ahead and then compute. So this is the solution of the Yang-Mills equations. And you can actually compute the initial energy density from the solution of these Yang-Mills equations. So this is your stress energy tensor. So this is the distribution of the energy density in the spatial XY plane, okay, at some given time. So this is a non-equilibrium simulation which tells you how you generate energy density and what it looks like spatially. And this is the basis of this so-called IP-Glasma model, where we can actually compute as a function of time these objects at some given time. And you can look at the eigenvalues of the stress energy tensor in terms of this contraction with a 4 velocity of these fields, which you can also compute, and that will give you the energy density. Okay, this is how this is extracted. So I compute T mu nu, I project that on the 4 velocity. Okay, this gives me an eigenvalue equation. Okay, and the eigenvalues are the 4 velocities, and the eigenfunction is the energy density. Okay, but now I can take this energy density and I can just match to hydro. I can say this is my initial condition. For hydrodynamics, what do I need? I need energy densities at every spatial position, and I need 4 velocities. Okay, and then I can solve my hydrodynamic equations. So I can do a brutal match of this initial energy density at some time to hydrodynamics, and that's the so-called IP-Glasma+MUSIC model, where MUSIC is the event-by-event hydro code that was invented by these guys here, Gale, John, Schenker. Okay? And so the combination of this is the IP-Glasma+MUSIC model, and it does a fantastic job of describing the data. So this is just IP-Glasma as a function of time. And you see that very quickly these fields, these gauge fields they lose their spatial structure. So initially, at some initial time, they have some nice spatial structure, which is anisotropic in each event when they collide, and then they lose it. While with hydro, it retains the shape very well to late times, okay, because there's strong interactions going on, okay, that maintain the shape. And so this is what gives you the VNs. So if you just did this object here, you would very quickly lose that nice spatial structure, while this actually will give you this very nice spatial structure. Okay, and so remember I talked about this phenomenology, and so here are the different flow harmonics in this IP-Glasma+MUSIC model. So these are V2, V3, V4, V5, okay, the Fourier coefficients of that particle distribution azimuth. And you see that for very low viscosities, viscosity to entropy ratios, you find very good agreement with this particle momentum. You can also do this as a function of centrality of the collision. So these are very peripheral collisions where the nuclei basically barely collide, right, overlap with each other, to very central collisions. And again, you see very good agreement with the data. You can also do much more differential stuff. You can look at the probability of having a certain V2 compared to the average V2 as a function of that V2. So event by event fluctuations in the anisotropies. And you see that this does a fantastic, the data is just beautiful from Atlas. And you see that these hydro models do a very good job. Now the initial spatial eccentricities are the ones in yellow that you see here. And you see that there's also a kind of nonlinear response in peripheral events where the hydro takes this eccentricity here and actually moves it rightward. So there's nonlinear hydrodynamic response that's involved in this, and that gives you a very good agreement with the data. So this has really been very successful. You can also think about the temperature-dependent AOS. When you do the same exercise at RIC and the LHC, you find that the model gives you a very good description of data in both cases, except in RIC. At RIC, you have to assume a smaller 8 over S. Okay, so at RIC, you have to assume 8 over S of 0.12, which is very close to this KSS bound, while at the LHC, it's about 2.5 times greater than the KSS bound. And so this is also another indication that 8 over S must be temperature dependent, right? So usually people put some constant value of 8 over S, but it's telling you that actually perhaps, the data are kind of telling you this, that you must have some temperature dependence in this 8 over S. And so that also then gives you a hint that you need to better understand the transport properties inside the Quark-Gluon plasma itself, and then you can try different parameterizations based on different models, okay? This is my last slide. I thank you very much for your patience to say, and this is something that I have to pay homage to Rob Pizarski, who actually first showed this slide, and I think it's very apropos. So this is, please claim credit, Rob. Just, I always tell people it's Rob. Okay, I have to. So now he's kind of ruining that for me. So you think of this, sorry, oops, okay, too late. Anyway, it tells you how ephemeral the Quark-Gluon plasma is. So I was going to say it's this nice golden unicorn you've been searching for all your life, right? And then you finally managed to corral it, But if you saw that the fence is kind of not very high, okay? And so you're not really sure that it's really the right thing, but you have actually localized this object, and now you can study, what its horn is like. Is it actually a horn or a whale's narwhal? Or a narwhal's tusk, or is it, what are the properties of this beautiful golden unicorn? So I'll talk about this more in my next lecture, and I promise you it'll be less equation heavy, but thank you very much for your attention.
Thank you, Raju, for this interesting talk. Now time for taking some questions.
Sir, if I understand correctly, the only parameter in IP-Glasma is this QS, which you obtain from Hera data? Or are there any other parameters? Because the way you showed, I think this QS is the only parameter.
That's right.
That is the only parameter.
And also the initial. So what you do in practice, so it's what you do is you use something called sort of Glauber Monte Carlo kind of thing, in which where you reproduce the Wood-Saxon's profiles of the nucleus by throwing nucleons in each event in such a way that they actually match the Wood-Saxon profile. But that's a very well controlled and understood thing. I mean, there are of course uncertainties in that, but those uncertainties are relatively small for the problem of interest. And so apart from that, the only scale that comes in is the scale QS. And that QS is again then fixed from data from deep elastic scattering. Okay, so what you do is you figure out what the QS is. So what you do is the following, right? So you do deep elastic scattering and you measure QS. Okay? From that QS, you extract what the color charge density is. Okay? So for each nucleon, you have a color charge profile. Then you take all the different nucleons and you construct your nucleus to match the Wood-Saxon profile. So in doing that, you've constructed then a color charge density profile for the whole nucleus. Okay? With that information. After that, all you're doing is solving the Yang-Mills equations with that color charge density profile. And that's the result. Okay? So that gets rid of a lot of parameters that people usually put in when they were studying heavy-ion collisions. And it's putting in physics at a sub-nucleon scale. Right? You're putting in the color charge distribution inside each nucleon, and then you're constructing the nucleus from all these different nucleons.
And another question.
Sure.
Can we apply this IP-Glasma to PP collision and then like this RG equation? So can it go down to like that level and be still true?
So this is sort of a usual thing in physics. You can always take frameworks which are well defined in one limit, right? So strictly all of this is really formally valid in some asymptotic radial limit of the theory, right? And very large QSs, very, very high energies, and all that. And then you can ask, and that's what we do in physics all the time, we try to extend the validity of this and see where the stuff actually breaks down. Okay? Now, sometimes it doesn't break down because it's accidental. Okay, and other times it breaks down and tells you really something interesting. So people have applied these things to PP collisions, and and they kind of do a good job, in some aspects. But it's really something again you have to always keep in mind, even for applying this to heavy ion collisions at sort of the energies that we are at. Is this really the appropriate framework for this particular kinematic regime? But it turns out that physics is only clean in certain limits. And that's also true, by the way, for all the stuff you heard about Hera and DIS and so on. It's all formulated in this Bjorkane limit of the theory. But then you start applying it to a few GeVs squared, and you don't really know, but then you say, hey, it works, right? But how do you know that it's working because effects are canceling among each other? So for example, in this structure function F2, you can actually show that higher twists actually formally cancel among each other between two different terms. Okay, and that's why in F2, higher twist effects are less sensitive. Okay, and that's why it works, okay, at low Q squared. But that's not really telling you the higher twists are not there, right? They're there in what you're doing. So this is a similar thing. So now in PP collisions, where such a framework might be especially valid is when you look at very high multiplicity PP collisions. So there are PP collisions that people do at the LHC and at RIC where you produce hundreds of particles. So it's almost like an AA collision in that sense. Okay, and in that framework, this kind of consideration becomes more appropriate.
And one last question. So this RG flows, so are there any fixed points? And I mean, because when I studied RG flows, so there are usually some fixed points in the parameter space. And
You know what? Give Edmo a hard time in his lecture next week and ask him that question. Okay? So, I mean, the answer is that we don't know for sure. Actually, I'll tell you my answer, and Edmond can vehemently disagree with me.
so if there is a fixed
But my, yeah, sorry, go on.
so like if there is a fixed point, then what would that, I mean, physically mean? I mean, if there is actually a fixed point.
Yeah, so in some sense, you can say that, you know, I didn't really get a chance. So I didn't really discuss RG in great detail in terms of the equations, but there's this equation called the BK equation, okay? And this is a nonlinear equation. I think I wrote that on the board, actually, yesterday. And so that has, in some sense, a non-trivial fixed point, in the sense that there's a fixed point when the amplitude is 0 or when the amplitude is 1. Okay, so these correspond to different non-trivial. So you can think of that in some sense as a fixed point. Okay, there's a larger sense in which, you know, whether the Jim-Wilk hierarchy or its generalizations flow to some fixed point of the theory. Okay, at very small x. Sorry. Yeah. I mean, but you know, yeah. But again, issues about whether it's really truly unitary, right? I mean, so Jim-Wilk is not really strictly unitary. But numerically, right, we know that miraculously, and also this was effectively explained in a paper by Edmo and Larry McLaren and Leonidov, right, that the theory somehow seems Gaussian in some non-trivial way, which is often an indication of some kind of universality. When you go to very small x. So what you can do is you can take these Jim-Wilk equations and you can solve them on the computer. You can compute endpoint correlation functions. And it turns out that the effective description of that, at least from numerical observation, is that the theory still looks kind of Gaussian in some non-trivial way. Okay? It's not the same Gaussian that you had, say, in the MB model, but you have sort of a more non-trivial kind of Gaussian structure there. So I think that's still a very profound and interesting question that's not fully addressed, I think. I mean, in terms of I don't know if you agree or not. But.
All the gauge invariant correlators with Wilson lines, they evolve according to equations which have the unitarity limit as a fixed point. Of course, Jim-Wilk as itself applied to non-gauge invariant quantities has inferior problems, so it was not a well-defined equation in that sense.
Yeah, but that still doesn't necessarily answer the question of whether there's a unitary fixed point.
Well, not in the sense of standard RG in virtualities, because it's not an evolution in virtuality. In the space of amplitude has a fixed point.
Okay, we can discuss this. You have to.
Yeah. I mean, Edmond, wouldn't you? I mean, when I would think of the fixed point, I would think of the traveling wave solution as a fixed point, actually, right?
Yes.
Talking about. I mean, so
yeah, that's what I'm talking about.
So, I mean, this is basically the geometric scaling fixed point, then, right? I mean,
that's where I was saying that BK.
So we should explain this too.
Has this kind of solitonic structure, but I don't think of that. To me, that's not as deep a fixed point as you would have, like a genuine fixed point, say, for example, in the vicinity of a phase transition, for example. Mm-hmm. Because BK is really about 2-point correlated with Wilson lines.
So it's a dynamical fixed point.
Exactly. I mean, and also it's kind of an unstable fixed point also in that sense. Well, okay, but that's still interesting. But I'm thinking really, and I think that's maybe perhaps where you're coming from, is that it's really a fixed point solution of sort of the entire effective theory, if you like, in the high energy limit in terms of all endpoint correlations, satisfy some scaling behavior, right? I mean, so I would describe a fixed point as saying, if I can define endpoint correlation functions, okay, gauge invariant or not, okay, and do they all satisfy the same scaling properties in some limit?
I think they do, in saturation limit, but you have to define them properly.
Yeah, okay. Well, I'll take your word for it. Okay.
More questions? If not, then let's say
One more. There's one more.
this there. Okay.
So I just want to ask one thing.
You can ask
So-
two things too.
They might lead to yes. So the thing is that we have the data available to us, and the way you are discussing is the initial condition setting up for the heavy-ion collisions, which is very important. Now, if the discussion of the V2 and all those harmonic moments which are there is very important, but the role of magnetic field, which is very large initially and then it decays down, that actually changes your initial distribution very strongly, because your radius is the particles are confined in a small radius, and so they are free to move in just the direction of the magnetic field and not in the perpendicular direction. And if it decays very fast, then suddenly that something which is confining them with small r is not there. And then they will have the freedom to move out. So how are we sure that this particular thing is not reflecting in the data? Normally people just look at it and say that it's the hydro behavior.
So firstly, I mean, when you talk about, so there are, like you say, and I will actually talk about that briefly in my last lecture. So there are strong magnetic fields. But the question is, what do we mean by strong, right? So these strong electromagnetic fields are on the order of, at most a pion mass. Okay, at tau equal to 0, they have the strength of the mass of, their typical momenta at most is that of a pion mass scale. So it's on the order of, m pi square, so m pi is 140 MeV. So you're talking about influence on scales, which is on the order of 140 MeV, okay? And so these fields decay very rapidly, okay? So on a time scale, when you're even starting to think about, 1/QS or time scales of that sort, and you're taking a production of, say, quark-antiquark pairs, which will feel those. Initially, these guys are actually mostly gluons, okay? So the quarks are actually produced on a time scale parametrically, which is 1/QS. By 1/QS, the electromagnetic fields are much weaker than the pion mass, okay, already. We're talking about GeV scale. The QS is GeV scales. We're talking about scales much less than 100 MeV. So that's a little tickle on top of what's going on. So of course, if you're able to, in heavy-ion collisions, resolve momenta scales, and that's an interesting question, is that if you can, have a very fine vertex detector and you can look at momenta below 100 MeV very well, then you may see the influence of these magnetic fields. And in fact, there are proposals at RIC and so on which have to do with looking at very small momenta to kind of identify these kinds of things. But it's very tricky because you also have the electromagnetic field of the detector, right? That's influencing this. So you have to really devise clever ways to cancel that out. But there's a strong push to actually measure these electromagnetic fields that one actually has in heavy-ion collisions, at RIC specifically. But for the scales of, several QS and so on, QS on the order of GeV and so on, this is a very, very small effect. It's almost negligible. Where the magnetic fields actually come in is in understanding topological effects, which actually originate in the infrared. And that's where it's very important. And I'll talk about that.
So
Fine.
essentially, if I take home point from this particular statement, could be that the initial magnetic field does not change my particle production.
It has very little influence on it, almost none. So in fact, you can actually do this calculation. So, and actually think about, the analogy to Schwinger pair production in QED, right? There the electromagnetic coupling is coming into the game, and that's a very small effect. So it's almost negligible.
Any more questions? If not, let's thank the speaker again.